Hey, good afternoon. This is No Smile John with Disruptive Weather, and I wanted to cover today's weather event, which is the nor'easter that is occurring on the east coast of the United States. Meteorologically, this is what we call a bomb or bombogenesis, and specifically what that references is when the surface low pressure decreases or strengthens in this case by more than 24 millibars in a 24-hour period. And we'll go over maps that show that occurring in the forecast models. But first, what I want to do is just take a look at what the observations were this morning. It's currently 5:40 p.m., the evening of the 22nd. Okay, so first I'm at the SPC page where they have both the 12Z and 0Z objectively analyzed maps based on the weather balloon launches that are twice a day at those respective times. So as I mentioned on my previous video case study, I always like to start up around jet stream level. That could be 250 or 300 millibars to get a rough estimate of what's going on up around 10 to 12 kilometers above the ground. So what you see here as we pull up the 12Z upper air at 300 millibars or 10 to 12 kilometers above the ground is that you can see here's a big, broad eastern U.S. trough. You have a little bit stronger flow out here off the coast of Cape Cod going eastward. And the yellow, that's indicative of divergence aloft. And then you can see the really strong flow coming through this jet and then even increasing as you go up into the purple shades up here off the coast. So you can see here all the yellow, that divergence aloft. You can think of it like if you all of a sudden pull air away from these regions aloft, there's only one place for the air to come from to replace it. So it's like a vacuum cleaner. It just sucks everything up from underneath, and that causes lifting motion in that area. So you can see the system right here at 300 very clearly. Another thing to point out is that with this stronger winds up here and weaker winds down here, that also helps this divergence aloft because you have air that's moving slower here than here, so you're effectively moving air away from this region quicker than you're bringing it in. So that's just something to point out that you do have upper level dynamics at play, not the most impressive dynamics that you can sometimes get with East Coast winter storms. And I'll go over this in some past case studies here in future videos. So the next map we're going to take a look at is the 500 millibar map. Now what you can see here is you can see the very strong flow coming around the base of the trough, a very subtle ridge, maybe more zonal right here, and weaker flow coming out. You can see that it's already closed. So you have a closed contour height here for 500 millibars, and I'll cover heights in some educational videos in the future, but just know that this is a really strong 500 millibar low. And we'll show this in some of the model analyzed data, but there's a really strong vorticity maxima associated with this strong flow. And so that vorticity maxima, I believe, is what's playing the biggest role in causing this massive bombogenesis with a major snowstorm on the east coast of the US. We go down to 700. So it's kind of hard to read, but you see those blue dashed lines and red dashed lines. Those are isotherms. Sometimes what we look for at 700 is when these wind barbs are crossing over those lines. And what that means is you could have air moving across these lines, which is referred to as advection. And if it's coming from warm to cold air, if the air is blowing from the warm to the cold, that's warm air advection, and vice versa. If you have warm air advection in a region, that is indicative of rising motion. We're looking at real winds here. What we look at meteorologically is a different wind called the geostrophic wind, and I'll cover that in another training. But for the purposes of this, we're going to make the assumption that the real wind is going to be resulting in the rising motion if you have warm air advection, and vice versa if you have cold air advection, sinking motion. So then going down to 850 again, this is around 1.5 kilometers above the ground. I can see a closed low. It looks like you have a low up here and then almost like you're developing a new one down here. And again, this is 7 a.m. this morning, so it hasn't even really gotten going in full force just yet. And then we can look at 925. You can see evidence of it starting the new low formation down here with the previous low back here. What this is referred to is you have primary, secondary. They have two types of East Coast winter storms, a primary, which is when you just have type A, primary type A, a low come from the southeast and go right up the coast and stays the same low the whole time. And then you have primary, secondary, where you have a primary low like this, and then you have secondary development on the coast, which ends up taking over and being the dominant storm. This is a primary secondary, and you can see that's occurring right here near the North Carolina coast at 925. And last but not least, here's the surface. You can see the surface obs. Temperatures are right around the freezing mark in the Northeast where the snow is projected to occur. So you can see that. You can start to see some of the wind coming out of the Northeast here down by Southern Virginia and Northeast North Carolina, and some of the wind coming out of the west. So you get the spin right there. I'm going to look at a different map to kind of see what the pressure analysis is off the coast. Through the model projection, okay, 18Z again, that's noon. So, and I said 21Z earlier is 4 p.m. It's actually 3 p.m. in the wintertime. When we switch to daylight savings, that's when it goes to 4 p.m. But 18Z, that's noon. And you can see there's the surface low. I'm going to go back up to 300 just to show how that changes over time. There's that wind that we were looking at on the 12Z. You can see strong wind up here. You can see another jet streak starting to form here, kind of a little weakness in between the two, but for the most part, it's not the biggest drop off. We're going to go forward in time and just show you how this progresses. You can see the trough really is getting well pronounced and sharper. As it's kind of taking on a negative tilt, you can see it kind of like a sharper trough right there pointing to the southeast. That's what we would call a negative tilt. You can see how the flow aloft, you have southeast winds over near Binghamton, New York of 40 knots. And then just over the Atlantic, just off the coast, you have south-southwest at, I think that's 100 and almost 140 knots right there. So you can tell that there's diffluence aloft where the air is spreading out right in this region. Go forward, you can still see it. You can see it really getting pronounced. You have southeast wind over New Jersey, and just over here south of Cape Cod, you have a southwest wind. So the air is really spreading out in this zone right here. Now you can see even at 300, the low closes off right here. That's really intense to see a low close off at this level. So that just is indicative of how strong it is. And again, you can see that spreading out of the wind. Okay, so now we're going to go down to 500. You can see here the 500 millibar flow coming in. Really strong flow. This is associated with a vorticity maxima. And we'll just step through. You can see how strong it is right here and then weakening up in this region compared to what it is down here. So really intense change in the winds at this level. Really see it right there. And you can see it's closed off a second contour at 500, which again, that's really intense. Even a third contour right there. So yeah, getting really, really strong. Almost 4 there. If you close that, you have 4 closed contours, but you have 3 closed contours in a real small distance right there. And last but not least, there's the 18-hour forecast for Monday morning. Here, bear with me. You can see how right here you have a low, and then you have southeast south winds right here off the coast, pushing warm air from over the Atlantic up into the region right along the coast. As you go in from the coast into Pennsylvania, eastern Pennsylvania, you can see the wind is blowing more parallel to the temperature change, and there's not much of a temperature gradient west of, say, about Philadelphia or so, maybe a couple counties west of Philadelphia. So the main area of interest is in this zone right there. Okay, here you can see warm air advection right over the New Jersey coast. As I mentioned, just west of Philadelphia. You don't have it because it's now parallel to the temperature contour, and the temperature change over this distance is very minimal. So you don't really have much warm air being blown over here in Pennsylvania. But over here, just on the coast, you can see all this warm air coming in right over New Jersey and just off the coast of New England and some up into Cape Cod right there. So you have warm air advection in this zone right along the coast. Going forward, you can still see some warm air advection coming into New Jersey, right off the coast, some right there by maybe Connecticut, Rhode Island, Cape Cod. You got warm air advection. So definitely some lift due to warm air advection in that region. It might not be that strong because the temperature gradient's not as intense across there, but you do have warm air advection resulting in lift over that area at 700 millibars. So now we'll go down to, I think I was looking at theta E, but that that that's kind of a good analogy as well still. You can still see the warm air advection using the temperature plot. Yep, warm air advection into New Jersey. Warm air advection up into southern New England at this time, which is 9Z or 3 a.m. Okay, so now we will go down to the surface. Well, let's look at 850 very quickly. Kind of the same as 700 millibars or 3 kilometers, but you can see that there is some warm air advection, but it's most confined to off the coast here. As you see, the winds on the coast are more parallel to the contours. So I'm not seeing a ton of warm air advection. There's maybe a little right there where you have a component to the wind that's perpendicular to the temperature contours. But for the most part, this doesn't have as much advection at the 1 to 1.5 kilometer level. So now we'll just go down to the surface. You can see how the low pressure is just around maybe 1,000 millibars. And then we'll step it through. 24 millibar drop in 24 hours is the definition of a bomb. So we'll just step it through. You can see it just got another contour there. That's 996. So every contour is 4 millibar difference. So still got 1,000, 996. And then you can see here, it's really getting strong over that 3-hour period from our 6-hour period from 6 p.m., just under 996. Then you go from 996, that's a 992 to 988 millibars right there in the center of that little circle. Then you see 992, 988. This is a 984 contour. Okay, so 992 is this one, 988, 984 is this one, 976, 972 right there. So we're already at 24 millibar drop. It's 1,000, 996, 992, 988, 984, 980, 976, 972. So we're basically going from around 1,000 millibars to 970, low 970s in under 24 hours. This is only 15 to 18 hours of being able to go that sufficient 24 millibars. So it's bombing relatively quick. It didn't even need the full 24 hours to do that. So very impressive. I'll just go through to the full 24 hour and you can see it starts to level out on how quick it's deepening. It seems to stop right around 970 millibars. Very intense low pressure system. All right, so I was mentioning earlier, I think most of the lift from this being caused by vorticity advection. So what I'm going to look at is 500 millibar is where we typically look to see vorticity advection coming into a region. And there again, there's math involved in this. I'm not going to get into all of the ins and outs in this presentation, but I do want to cover that this is what is likely the biggest culprit for the strong strengthening of the low, as well as the heavy precip that occurs along the coast. So if you watch, what we say is when you have the wind blowing vorticity into a region, that's cyclonic vorticity advection coming into a region. When you have advection of cyclonic vorticity, which is these reds and purples and yellows coming into a region with not much vorticity, that is a very favorable area for lift over the region. And that can lead to very strong precip and strengthening of the low when you have this intense of a vorticity max coming through. So let's just see as it comes through the whole time. And look at that. Look how strong that vorticity is right there, coming right up here, the wind blowing it north right there, right over New Jersey and the coastline. And you can see that continues here. And so now you have vorticity advection coming into this region from the east. And all along here is positive vorticity advection or cyclonic vorticity advection from the southeast. So let's go back to I think it was the 9-hour. So yeah, if we look at this one, this is about 6 kilometers up. Let's go to about the 3-kilometer level and look at vertical velocity. So this is upward motion in the area. It'll show where you have upward motion. So remember, right here is where the vorticity is being blown into the region by the wind. So look at all that rising motion right there on the coast and just north of where that strong vorticity is. So you have the vorticity down here. You don't see a lot of rising motion down there because it's already reached its maxima. The vorticity is moving into this area. Vorticity is just spin of air in a region. So that just kind of gives you an idea. You can see right here, compare that to the 500 millibar vorticity. So right in this region's where you have the strong rising motion. Just off the coast, right where that vorticity advection is. But then it goes up into Connecticut and Rhode Island, the rising motion. And let's go look at vorticity. You still have vorticity advection coming in just off the coast here and still ongoing right there. So let's go down to the surface and look at the precip at these various times. This is composite reflectivity, so I'm just going to step through. If you recall, 9-hour and 12-hour over New Jersey was really heavy, so there you go. Lots of precip right on the coast. Yeah, so that and it's all falling as snow at this point. So one last thing I want to look at here is down at the surface winds, just to show you why this is another factor that's really playing a big role. So over the water, you don't have a lot of friction as you do over land. So a lot of the wind over the ocean is a lot stronger. And when that slams right into the coast, you can get coastal flooding along with blizzard conditions if you have snow right in that region. And that's exactly what this is happening here. So you can see all the strong wind all along the coast. And hence why, if we go look at the National Weather Service, they have blizzard warnings all in this red up here. So if we look right here in New Jersey, it'll also show us we'll look at their snow totals, but you can see the blizzard warning goes from Philadelphia all the way to the coast. Notice I mentioned there was less warm air advection out here. You do still have maybe some contributing upward motion due to vorticity advection over the region, but for the most part, the strongest combination of all the factors that are causing lift is occurring right here. And so now let's come down here and look at their expected snowfall totals. As you can see here, right along the coast, they are expecting 24 to 30 inches. So this is definitely a disruptive system, and why we're covering it being disruptive weather, because this is really going to disrupt the beachgoers um, on their summer vacation next week when they go to the beach. So I feel sorry for all these people. They may have to make new plans for their summer vacation with all this snow occurring on the coast. Similarly, we'll go up to New England and see the what they're forecasting up here. You can see they have a civil emergency message for the whole state of Rhode Island. We'll take a look at that here in a little bit and see what that's all about. But I want to look at the snow forecast. You can see 18 to 24 common throughout southern New England, from Boston down to the southeast portion of Massachusetts. You can see out on the Cape, the amounts are less. That's probably because they're mixing with sleet and or rain. And then you can see Connecticut solid 12 to 18 over the whole state, with some areas being 18 to 24. You can see down to like New York City and Long Island, 18 to 24 inches of snow as well. So let's go see what that civil emergency message is for Rhode Island. Okay. Whiteout condition, blizzard conditions and whiteout conditions make travel treacherous and potentially life-threatening. Travel ban starting 7 p.m. today. Wow. So the high winds, snow could bring down trees and power lines. Yeah, not good. Definitely disrupting. If you don't have your bread, milk, and eggs by now, I don't know how you're going to survive this storm. That being said, on the breadometer, I would give this probably a 10. The combination of the very strong winds and 2 feet of snow definitely justifies a 10 on the breadometer. So please be careful. Definitely an impactful, disruptive winter storm. I feel sorry for the beachgoers. You're not going to be able to work on your tan. Um, yeah, it's bad, and you better have all the bread, milk, and eggs you have so that you can make your milk sandwiches and scrambled eggs, because I just don't see how you would survive. That's all for today, and as I mentioned, East Coast winter storms are what got me into meteorology, so this is definitely fascinating for me. Rather than worried about the forecast, because the models do a lot of the forecasting, I like diagnosing what's actually happening, and that's what I did here. Now, sometimes I will just say, hey, let's look at the forecast. You see how it pans out. We did cover some of that, how it's going to look for this region in southern New England. And because it hasn't really started full force in that region just yet, but it will. And that's what the model was showing us in the future forecasts. That's it for today. Please, if you like this video, click the like button. And also I ask that you subscribe to Disruptive Weather. Again, this is No Smile John signing off.